Hi, we're going to look at critical points. So if a function f is defined at x equals c and f prime of c equals 0 or f prime of c does not exist, then our function f has a critical point at x equals c. Because we know essentially our f prime of c is our slope of c. So this is essentially saying if we have a slope of 0, so that'd be a place where our graph changes direction. So for example, in this case, this would be our c value. And what we would find is we would essentially have, if we have a f prime of 0, then that means we have a horizontal line. So that would be our point at which our graph changes direction. So this would be if f prime of c equals 0, we have a place where it changes direction. So therefore, we would have a maximum or minimum value at that point. And this can also be referred to as a stationary point. This one, our c value would be right here. And this would be if we have f prime of c is undefined. It essentially means at that location of our graph, we have a non-differentiable point. It could be because our graph is not smooth at that location. It could be because we have an asymptote at that location. Now, to find our critical points, we're going to, because our definition of it includes our f prime either equaling 0 or does not exist or undefined, we're going to take our derivative of our equations and find where it is equal to 0 or it is undefined. So we'll look at an example or two. So find all critical points of the following functions. Our first function is y equals negative 6x cubed plus 18x squared plus 3. So we'll take the derivative of this. So when we take the derivative of x cubed, that's 3x squared. So when we multiply that by the negative 6, that gives us negative 18x squared. Taking the derivative of x squared is 2x, so multiply 18 by 2, so plus 36x. And then we have derivative of 3, which is just 0. So we currently have this function. So what we'll do now is we'll factor this. You'll notice out of both terms, we can factor an x out, and we can also factor 18. I might as well factor negative out as well. So I'm going to factor out negative 18x. That's going to give me x minus 2. Now we're looking for where this function equals 0 or is undefined. In this case, there's not a location where it's undefined. So we can say x is equal to 0 and 2, and these are critical points. So in this case, because they're not undefined, these would be locations of either maximum or minimum values. So one is likely a maximum, while the other is likely a minimum. Next, we've got y equals 3 times x to 2/3 minus x plus 1. So we're going to take the derivative of this. When we take the derivative, this 2/3 will move in front. So 2/3 times 3 would be 2. And then we're subtracting 1 from this, so this becomes x to negative 1/3 minus derivative of x is just 1. Derivative of 1 is 0. So we'll just rewrite this in radical form. So this would be essentially 2 over the cube root of x. Minus 1. Now this one's going to be a bit harder than the previous one to find critical points, but right away from looking at this, we know that x cannot equal 0 because we cannot divide by 0. So this right away tells us x is equal to 0 is a critical point. Now, because this one was defined by x cannot equal a value, this would be something like an asymptote. Now we want to find what value of x makes our equation equal 0 to find a maximum or minimum. So if we'll put 0 in, so we've got 0 equals 2 over the cube root of x minus 1. We'll move the 1 to the other side, so 1 is equal to 2 over the cube root of x. Multiply both sides by cube root of x, we get cube root of x equals 2. So therefore, x is equal to 8. So this would be our other critical point, which would be a maximum or minimum. Next, we'll quickly review interval notation. So in interval notation, we list our leftmost point first and then our rightmost point. And those are separated by commas. Now, around those points, we have brackets. Square brackets we use if the point is part of our solution, so a closed interval. And round brackets is if a point is not part of a solution, so an open interval. So we're just going to do an example of writing the following as inequalities. So this one had nothing but square brackets, so that means that term is part of our solution. So we'd have 2 is equal or less than x, which is equal or less than 4. This one has rounded brackets, which indicates that these are not part of your solution. So therefore, this would be negative 1 is less than x, which is less than 8. So you see the difference between these is these inequalities have are equal to because of square brackets, which means those terms are part of our solution, where these ones don't have equal to because of these round brackets where these two values are not part of our solution. We can get infinitesimally close to them, but never exactly equal to them. Now, in this case, we have a round and a square. So therefore, we know 5 is not part of our solution, so it will just have is less than, while our 25 has less than or equal to. Now, if we have something like negative infinity or positive infinity, we don't tend to put that value into an inequality. Instead, we know that we're going all the way to negative infinity with a maximum value of 3, so we'd have x is less than 3. This one, we have a minimum value of 5 and we go to infinity, so we'd have 5, and because it's square bracket is equal or greater, or sorry, x is equal or greater than 5.